Okay, so first of all, whenever you're doing any kind of Euclidean geometry, it kind of builds on top of each other. All maths does, but Euclidean geometry in a big way. We expect you to know all your properties of your triangles and your things. When you see parallel lines, we need you to know that you've got alternate and co-interior. And this is basically what the flashback is all about, because you need to remember all of that all the time. And it's a summary that you can build on as we go through. So if we have a look here, sorry, I'm just changing my mouse. Okay, so if we have a look over here, this is basically talking about our alternate and corresponding and co-interior angles. The biggest thing that we always forget is, remember, co-interior, they actually add up to 180, whereas corresponding and alternate are equal to each other. Your triangle, the angles inside a triangle add up to 180. If you've got an isosceles triangle, remember to please use the correct reason for equal angles. So angles opposite equal sides. And then you've also got the exterior angle of the triangle, which a lot of people forget. And then your right angle triangle for Pythagoras' theorem. That is also always useful. Okay, and now we're going to be starting with our first lot of new theorems and new knowledge that we get from grade 11. Okay, so starting here with theorem 1, it's line from center perpendicular to a chord. So basically what it's telling us is that if you've got a line from the center of your circle going to a chord and it's at 90 degrees, okay, then that is going to bisect the chord. So it's going to cut it in half. So a line drawn from the center of a circle perpendicular to a chord will bisect the chord. So basically what would be happening is we'll land up that NM is equal to MP. And the reason you use for that is this thing that they've got in brackets. Line from center perpendicular to chord. Okay, that's the reason that you would use. Guys, you'll notice at the beginning of your course notes, there's a whole lot of sort of allowed reasons. So it's a list of statements and reasons that you can be using in your, that are considered appropriate for your geometry. So please reference that. If you have been told to use a different reason that makes more sense to you, please reference that list and check that it is on there and make sure that it's okay. Okay, so that's basically what this theorem is going to tell us. And you can even experiment with all these theorems and try and draw it accurately. So if you were to draw a circle and draw a line from the center and then draw a chord across, that's definitely at 90 degrees, a perpendicular line going across that. You can measure it and find out. So they're fun theorems to just sort of play with and actually draw them. Okay, so this is the proof for the theorem. It's good to sort of get used to our old geometry that we needed to know to be able to prove these theorems, as well as they are examinable. So I think they often test either theorem 1, theorem 9, and I think the other one's theorem 6. I can't remember the number. I'll remember when I get there. Okay, so join OM and OP. So this is the big thing whenever you're studying these, guys. So studying a proof of a theorem, the good thing is usually when they ask you to prove a theorem, they say prove the theorem that states, which kind of tells you it's one of the proofs that you've learned. And it should be free marks. It's considered level 1s. Okay, but don't try and learn the theorem off by heart as you see it here in front of you. Because if you try and learn it off by heart, they're going to have changed the letters. You're going to land up leaving out a line, which means it doesn't flow anymore. And then you'll end up losing marks that you don't need to lose. Okay, so rather learn the process. So if you want to prove this, the first thing you're going to learn is your construction. And your construction in this case is going to be join the radii. I'm not going to give them letters because in the test or exam, they're probably going to use different letters. Okay, so you join the radii, and that's this first step here, joining OM and OP. Sorry, it should be ON and OP. So you would draw that in, and you actually tell them construction, I'm drawing OM and ON and OP. Okay, the next thing you're going to learn is the method that you go about from there. So that's this step over here. Okay, and that's basically how we're going to prove it. We're going to prove it by congruency, RHS. I'm not going to try and learn every step. You guys should know how to prove two triangles are congruent. Okay, that's grade 9 work. So that we're not stressed about. We're going to look at the picture and see how to prove them congruent. But if you know that that's what you've got to do, that's a lot easier to learn off by heart. Oh, I've got to do congruency. And then you don't have to worry about trying to remember all the little bits. So you can see here the proving congruency. They're focusing on these two small triangles here on the sides. Okay. The first thing they said is the two M values are equal. Why? That's because the lines are perpendicular, so they're both 90 degrees. And because we're using right angle, you should actually tell them that it's also 90 degrees, okay? Then you know that the radius of a circle is going to be the same wherever it is. So those sides are going to be equal because of radii. And then lastly, this line OM is common. So there I've got my right angle. The radii were hypotenuses of the triangles. And I've got another side, RHS, which is why I can finish off with my statement. Because those triangles are congruent, it means that those sides there must be equal to each other. Okay, so this is one of the proofs that they can test. Guys, don't try and learn every step off by heart, rather learn the method. So construction, you need to know that because that's your starting point. And the next thing, what method am I going to use? I'm going to do congruency with right angle hypotenuse side. If you struggle to remember the theorem from there, you can start doing things and saying, okay, well, I've got to use my radii, and please remember that you've got to use your 90-degree angle. So you can give more detail if you're struggling, but otherwise that's really all you need to try and learn off by heart to do the proof, because you guys know how to do congruency. So we don't need to do more than that. Okay, so are we all happy? Do we understand what was going on in the proof here? Please take note of the typo that I pointed out to you. I don't know, sometimes it's just in the PowerPoint, but that joining, it is actually ON and OP. It's joining the radii. Okay, and then we're going to have a look and see how we can use this. So basically, if we've got a line from the center going to a chord, remember a chord is a line going across from one side of the circle to the other. I actually just realized we possibly need to have a look at all our terminology and make sure we're all okay with that. Are there any questions here? Okay. Mpendulo, I see that you're unmuted. Do you have a question? Okay, I'm taking the muting yourself as a no. Okay, so guys, I just want to make sure that we understand our terminology because I realized we actually haven't revised that, and this is new for you guys. So I'm going to quickly just go to a blank screen so we can go through all the different terminology that we're going to be using a lot of in these formulae. Sorry. Okay. So if I've got a circle, sorry, it's not a very beautiful circle. Drawing a line from one side to the other side, we call that a chord. Okay. Then obviously we all know what the center of the circle is, so we shouldn't have an issue with that. The radius of a circle is the line from the center going to the circumference. And a diameter is going all the way across through the center. Okay, so it's a chord, diameter, center, and radius. Okay, the next thing is you get an arc, and you get a segment. Okay, so this here, if I've drawn that chord that I've drawn there, then the arc that we'd be talking about, if I were to call it A and B. Okay, so we've got chord AB, but in green I've highlighted arc AB. Okay, but theoretically I could also look at the other side and say that this is also arc AB. So then we sometimes differentiate between a major arc, which is the bigger one, and the minor arc. If a person doesn't specify if they're talking about the major or the minor, then they're always talking about the smaller one. Okay, and then the last thing that we've got to talk about that they often reference is a segment. Okay, and that there is like the bit that you've cut off of the circle, that is called a segment. Okay. Okay, so that's basically the terminology we're referring to. So at the moment, we've basically just used the chord and then a line from the center. The line doesn't have to be the radius. It doesn't have to be the diameter. If you think about the diagram that we did just now, it was literally from the center going to the chord perpendicular. So it wasn't a full radius. Okay, so we've just used the word chord so far, but I will remind you as we're going if there's anything that confuses you. Okay, so let's go back to those course notes. Okay, and here is still theorem 1, but slightly different version. So theorem 1 almost comes in, well, it does. It comes in 3 different versions, depending on what information we're using, and each one needs a different reason. So as much as it feels like it's the same theorem, guys, you need to make note of it because each one's going to use a different reason. Once we've done all 3, I will give you more explanation as to those different reasons. So this one now is saying I've got a line from the center and it is going to the midpoint. Do you see that KL is equal to JK? So the last one was a line from the center and they told us that it was perpendicular. Okay. This time they're saying we've got a line from the center and it's going to the midpoint. And if it's going to the midpoint, then you know that it must also be perpendicular. So it's still the same 3 concepts. It's from the center, the midpoint, and perpendicular. So at the end, you've still got all 3 wrapped into one. And here, let's have a look at the example that they've given us. So given circle center M, so they've told us that that is a center. Whenever they give you information in geometry, it's for a reason. So that means you need to use the fact that there's a center there with a diameter of 20 centimeters. So if the diameter is 20 centimeters, it means that my radius is 10 centimeters. Notice I'm looking at all the information they've given me before I'm even reading the question. Okay, don't jump straight into the question. Make sure you know what they've given you first. And then the chord DF is 12 centimeters. So they've told us that DF is 12 centimeters. I don't like writing those measurements on my diagram straight away because if I put the 12 here, then when I'm starting to think about it, I might think that I'm just talking about DE. So do what you need to do to remember it. Maybe highlight DF so you remember that you've got it. And it says here, determine the length of chord AC. Okay, so they want us to find chord AC. So there's 2 things we're going to remember. If we've got a line from center perpendicular to chord, okay, so if we've got that, then we know that it's going to be at the midpoint. And then the other thing that we've got is if we've got a line from center to the midpoint, if they've given us that, then I know that the lines are perpendicular. Okay, that's probably not the best way to write it. This will be better. Okay, that's what we know. So I want to find out if there's anybody. Amakle, I see you've got like a tick notation. I don't know if you're trying to get my attention, or if it was an accident, or okay. Awesome. Okay, I want to find out if there's anybody who is brave enough just to tell me what they know from the stuff they've given me. That you don't need to give me the final answer. You guys have the final answer in your notes, but I mean, the point is I'm trying to work through on how we would get there. Okay. Does anybody want to just tell me what they can pick up from the diagram and from what we've been told? Or even work through the answer with me? Is it still too early? We're not brave enough. You can do it in the chat if you want. Okay, we've got somebody who's telling me that MA is going to be 10 centimeters. Yes, because MA is a radius. So let's fill that in. That's easy enough. That's not going to confuse me. It must be talking about MA. FM is equal to AM. FM is equal to AM. Yes, because it's also a radius. So I'm going to put another 10 there. Okay, so I've been asked, can we use Pythagoras? Guys, we can use Pythagoras, but only if we've got a right angle triangle. So always just double check. And yes, I think using Pythagoras to get x would be a brilliant idea, because if we have a look here, this is definitely a right angle triangle. Hope you can see that yellow. It's not coming out clearly on my screen. Okay, we've got somebody saying EF is equal to 6 centimeters. Okay, EF is equal to 6 centimeters, but they didn't actually give that to us. So this is the first time. Yes, you're correct. You're definitely not incorrect. But this is the first time that I'm actually getting to start using theorems. At the moment before that, we were just putting down information that we had seen. So the first thing that you guys have told me, the way I have to actually write down EF is going to be equal to 6 centimeters, but we've got to explain why. And the reason we know that this is 6 is because we know that that had to be a midpoint and each side was going to be 6 because the whole thing was 12. So it's using this bit over here. It's a line from the center perpendicular to chord. So line from center perpendicular to chord. Okay, notice that my statement refers to the midpoint. So remember I said we always got to use the correct reason. So I want to make sure the statement is using the midpoint. And then my reason is talking about the center and the perpendicular. So I've used midpoint, center, and perpendicular. You've always got to have all three. Your statement and your reason together must mention all three. Okay, so now that we've got the 6 and the 10, earlier we were told we should use Pythagoras to get EM or to get X, and that's exactly what we can use now. Because we've got a right angle triangle, 10 squared is going to be equal to X squared plus 6 squared, and that's because of Pythagoras's theorem. It is Euclidean geometry, so please give me that reason as well. Okay, so I've had a question about whether or not the chords can be different lengths. Your chords can always be different lengths, and I'm going to just quickly, while you guys are solving for X, I know I've got one answer there from Shristi. Okay, and Zananpolo has also now given me an answer. I hope I put the click in the right place. Okay, so here you can see there's a chord there, chord AB. But a chord just means it's going from one side of the circle to the other. It doesn't have to go through the center, but we can do that anywhere we want. And I'm hoping you can see that chord CD would be longer than AB. So a chord is not in a specific position where you're cutting off the circle. It could be anywhere, okay? And you could even put another one over here, EF. And obviously, as you get closer to your center, you'll get the diameter, and the diameter is actually just a special kind of chord. It's the longest possible chord you get. Okay, so yes, your chords can be different lengths, So we can't assume that the two chords are going to be equal. So when we work this out, you're going to go 10 squared minus 6 squared, and then you're going to square root, and you should land up that x is equal to 8. Are we all happy with how we found out what x is going to be? Great. Simpu, I'm glad that made sense. Awesome, and I got a thumbs up. Okay, so now we're carrying on. So we know that this is going to now have a distance of 8. Remember another thing in geometry? As you go along, you always fill in the information that you found out because it might help you later. Okay, so if we know that x is 8, what can you guys tell me about MB? If we know that x is equal to 8, what's MB going to be, or BM? Yes, there we go. Thank you, Zanel. Thank you, Bongeka. And Michelle, thank you. Okay, so BM or MB is going to be 8 minus 3, because it was x minus 3, which gives us 5. That is just substitution, it's just algebra. It would not have a reason. Okay, so we know that that's going to be 5. So then I put that on my diagram. Okay, but we still remember we're trying to get to AC. So we know that this is 5. Okay, so what's the next idea? So now we've got MB is 5. We're still trying to find the length of AC. Any ideas? Michaela? Michaela? Michaela, you're unmuted. There we go. Okay. Okay, so a couple of you have said use Pythagoras. Guys, please remember, because this is one place where a lot of people lose out marks here. Yes, we're going to use Pythagoras, but we can only use Pythagoras if we know it is a right-angled triangle. And at this point, if I look at this right-angled triangle over here, if I look at that, it looks like a right-angled triangle, but I don't know that it's a right-angled triangle. So I've already been given a hint by Michelle that we have to still first say that it's perpendicular, which is right. You have to prove that it's right-angled before you can start. And then you can start using the theorem of Pythagoras. So the first thing you're going to have to say is that BM is perpendicular to AC. And how do we know that? We know that because it's a line from center to the midpoint. Now remember I said if you're trying to figure out which reason you need to use, remember your statement together with your reason has to mention all three aspects. So do you see here we're talking about the perpendicular in my statement, and in my reason I'm talking about center and I'm talking about midpoint. So I've mentioned all three things, and that will help you to figure out which reason to use. That is very important. Now that we know it's 90 degrees, we can use the theorem of Pythagoras to get AB, which a whole bunch of you have said. Okay, so I'm just reading a comment, so you guys can do the Pythagoras first, please. You guys should be able to do Pythagoras for that pink triangle for me and find the length of AB while I'm reading a question. And you can pop in the chat when you have your answer. A and D is less than or equal to MBA. It's less than or equal to MBC, which is equal to 90 degrees. Okay, so Michelle, I think that you're trying to prove that it's 90 degrees. I'm not too sure your logic actually follows though, so we'll just use the theorem. AND, did you mean AMD? I can't see the N value. Okay. So Shristi's given me decimal places for an answer, let's have a look. So we're going to have 10 squared is equal to 5 squared plus AB squared. My reason, don't forget your reason. Okay, Bongeka agrees with Shristi. Okay, so that's going to be 100 minus 25. So basically AB is going to be equal to the square root of 75. Or you could write that as 5 square root 3, which I'm assuming is 8,66. Okay, I wouldn't use the decimals until the very end if they've asked for decimals. And I'll tell you the reason, because you don't want to round off early. So I'd rather type in 5 square root 3, and then your calculator gives it to you like that. I'd rather type in 5 square root 3. Okay, but AB is the same as BC, so then from here, therefore AC is equal to 10 square root 3. And they didn't say anything about decimals. If you gave it to decimals, 2 decimal places, that's fine. If you left it in surd form, that is also fine. Okay, I scribbled all over the page because I feel like explaining and working through it makes more sense than you just seeing the answer. So I hope that was useful. I'm about to clear it though, so let me know before I clear it if there's anything that you're concerned about. Do you understand why I used the 2 different reasons? Okay, over here, I used the line from center perpendicular to chord, there line from center to midpoint. Make sure you understand why we use the 2 different reasons in the different places. Okay. I always assume that the silence means that everything's good and I can move on. Okay, so let's clear all of this. And there you can see they've given you all the answers. They gave it to you in decimal places, which is 17,32, which was double 8,66, which Shristi and Bongeka gave us. Okay, and then this is the 3rd version. As I said, there's 3 versions of the same theorem. And this time you'd say the perpendicular bisector of the chord. So if you've got a chord, so here my chord is PT, and I've got a line that's going through that chord, but it cuts it in half and it is perpendicular. That means that this line does go through the center somewhere. I don't know where on the line the center is going to be, but it does go through the center. And you can see that they've got the proof for this one as well. It says choose any point, M, and then you're going to join the MT and the MP. So you're kind of joining what looks like radii. So again, we're not going to, when you learn your proofs, guys, please do not try and learn the whole thing off by heart. We'll learn your construction. So the construction, what you'd actually be studying here is join, and they're not really the radii because we don't know where the center is. So I'm going to say fake radii. So basically you choose a point that you think is the center and you join those, okay? And then again, you can see they're going to follow congruency. Let's do that in a different color. So then the method you follow after you've done that construction is you're going to do congruency, side angle side, and that congruency tells me that these 2 points are going to be equal, that MT is equal to MP. But all points on AD are equidistant from P and T. And the center is equidistant from P and T. Therefore, the center lies on AD. Okay, so this is kind of like a conclusion, which probably is going to be difficult to remember. So your conclusion would possibly be the 3rd thing that you make sure you understand how to wrap it up. Okay, so that's the proof. Notice that this reason is different. Perpendicular bisector of chord. So let's see if we've got an example for that. Okay, we don't have an example for that, so I'm going to quickly just make sure we've got all 3 of these things, and when we'd use which reasons. Sorry, that's why I'm confused, because I'm looking in the wrong place. Okay. Okay, so we've got three different, from theorem 1, we've got three different reasons. Our first reason is line from center perpendicular to chord. Our next reason is line from center to midpoint. And our last reason is the perpendicular bisector of the chord. Okay, so if I had a circle here, the first one, line from center perpendicular to chord. So there's my chord and I'm drawing it perpendicular, and my statement would be that AB is equal to BC. Okay, AB equal to BC. See, the statement talks about it being in the middle, and the reason is the center and then the perpendicular. Sorry, I underlined the wrong thing, and the perpendicular. Okay, the next option we might have here is a line from the center going to the midpoint of the chord, D, E, F. So my statement here would be that ME is perpendicular to DF. Notice I'm talking about the perpendicular in my statement, and in the reason I'm talking about the center and the midpoint. So I've used all three concepts. Okay, the last one, I don't know where my center is. I've just got a random line going through my circle, but I know that it's cutting a chord in half and that it's perpendicular. KL, we'll call it. So here your statement would be something like KL is a diameter. And you're going to realize why it's so useful to know when you've got a diameter later when we do more theorems. Okay, so here you would say something about KL being a diameter. So that tells you that it's going through the center. So my center is in the statement, and then the perpendicular and the midpoint are mentioned in the reason. So it's the same theorem with three concepts, three different reasons depending on how you're using the theorem. Okay, so I hope that's made it clear as to when you're going to use the different reasons. Okay, let's go back to the PowerPoint. We've got a whole bunch of theorems that we're going to be learning today. So that's just the first one. We've got 9 of them. So let's go back to the PowerPoint and have a look. So this is the converse of theorem 1 still. There you go, theorem 2. Angle at the center is equal to 2 times the angle at the circumference. Okay, so over here, and I usually sort of show it with my fingers. So I would put my fingers where the 2 points are on the circle, and I follow from those 2 points, and if I can go to the center, and then I'll go back to those points and I can go to the circumference. That's what tells you which 2 angles you're talking about. So you literally put your fingers on point A and B, and you follow the lines and you get to the center. If you can go from A and B and also get to the circumference, that's what tells you which angles we're talking about. The PowerPoint is not showing, okay, because I just clicked there. Thank you very much. Is that better? Thanks, guys. Okay, so now you might have more sense of what I'm trying to say. You would put your fingers on A and B, and if you follow the lines and you get to the center, which in this case is at point M, and then you go back to A and B and you follow the lines and you get to point C, okay? That is how you figure out which angles we are referring to. So this one here would be the angle at the center, and that one there is the angle at the circumference. And the reason that you use, so it's always these ones in brackets up at the top. is always angle at center equals 2 times angle at circumference, and that tells you what calculation you need to do. Now, basically, you're either multiplying by 2 or dividing by 2. So if you remember that the one at the center is always the bigger one, it lands up being useful. Okay, it lands up helping you to remember, am I multiplying by 2 or dividing by 2? But otherwise, substitute in, this is basically a formula. Your reason is a formula. And if you substitute into there, you won't go wrong either. Okay, so this is another one where they're going to give you the theorem. So, I mean, the proof of the theorem. So you can see here, they're first talking about AM equals to BM equals to CM. So what they've done, again, please remember your construction. So your construction is going to be from center, you draw a third radius and you extend it. So you actually go past, so you're kind of cutting through both the angles through the center, and you don't have to go all the way across, but you do have to go past the center because you're trying to create a little M1 and an M2 and a C1 and C2. Okay, once you've done that, what you're going to learn from there is you're going to use the exterior angle of triangle. That's basically what you're going to be using. And once you know your method and your construction, you should be able to prove it because it's just all your normal geometry. Okay, so that's the proof. Guys, I wouldn't stress too much about the proofs. I'm kind of going through them. I'm trying, and I'll stop actually going through them when we get there later. I just want you to realize if you do, when you're studying the proofs, not to try and learn it off by heart, learn the method. Okay, but there's going to be a lot more marks in understanding how to use them. So we're going to practice that more than actually going through all these proofs. I don't want to spend too much time going through the proofs. Okay, so here's an example. So you can see that there's 2 points. Well, there's actually 3 points on the circumference. There's D, E, and F. Okay, so we've got 3 points. We've got D, we've got E, and we've got F. So you've got to find 2 points that if you put your fingers on, they're going to go to the center. And if you put your fingers on them again, they go to the circumference. And you can see that is E and F. So the first time you put your fingers on E and F. So that's where your fingers are. And you follow your fingers to the center. And that gives me my angle at the center. Then you go back to E and F. And you follow lines to get to the circumference, and that gives you the angle at the circumference. And then you know that the angle at the center is equal to 2 times the angle at the circumference. So the angle at the center is 54 degrees is equal to 2 times the angle at the circumference is x. And that is your reason. Angle at center equals 2 times angle at circumference. And then you can solve for x. Okay, I hope that was okay. I think there might be another one, so they do have that all written down for you in your notes. Okay, here's another one. And after this, we're going to take a short break. So I want you guys to have a look and try this one. It's a little bit trickier. Okay. So starting off, 2 points where we're going to the center. Okay. So over here, if I put my finger on those 2, I go to the center and I get O1. Okay. So I've already got an answer for 44 degrees for x. And yes, your answer is correct. And I see you guys aren't even using the new stuff because that doesn't use the new stuff. So that's perfectly fine. Okay. Now, I just want to look at our options. So if we did the A and D, can we go from A and D and also go to the circumference? So is there anywhere where we can follow from A and D and also get to the circumference? And the only place I could sort of see that I could go is down here. The problem is they're on different sides, which is a trap that we all fall into. So you feel like that's the center, that's the circumference, but they need to be on the same side. And I just want to make sure I explain that to you because it lets you know that we have to do other things. Okay. So the first one we did looked like this, where that was the angle at the center, that was the angle at the circumference. Do you see that both angles are sort of underneath the vertex? Okay, whereas what I've highlighted now gives us a problem because they've actually gone this side. And do you see the angles? An angle at the center is underneath the vertex. The blue angle I've drawn is above the vertex. So they're in a different position. So I need you to be aware that when we're talking about angle at the center equals twice angle at the circumference, that is part of what you've got to be careful of. Okay. So a lot of you have said 44 degrees. Some of you had said radii. So I know you've done different ways of getting there. So I'm going to not give the step-by-step reason for it, but I'm going to just tell you what the people are saying. So if this is 88 degrees, I know that those two are equal because they must be the radii of the circle. Okay. That means that this guy over here is also x. So that's using exterior angle of triangle. I know that 2x is equal to 88 degrees. Okay. And that's definitely one way you could have got there, and that is perfectly fine. But because I want us to practice this new theorem and I want us to spot it if it does come up, I'm going to go back to this new theorem. So basically, if you were to put your fingers on the point A and point C, I can go to the center from A and C, and that is 88 degrees. Okay, I can also from A and C go to the circumference, which is x. So using our new theorem, which I'm not saying you have to do, but I want you to be used to seeing this theorem like this. Okay, you know that the angle at the center is equal to 2 times the angle at the circumference, which again gives you x is equal to 44 degrees. Angle at center equals 2 times angle at circumference. Okay, so we know that that is 44 degrees, and I've got some answers of 134 degrees for the y value. Okay, so we'd have to look at how we get to the y value. I'm giving you guys a chance to think about it. I don't want to just give you the answers, and I know you got the answers in front of you guys, but don't cheat. So Michelle, tell me either by texting or unmuting, whatever you're more comfortable with. How did you get to 134 degrees for y?
Ma'am, I know that y is equal to, y is half of O reflex. So meaning
O reflex, okay, this one here.
Yes, ma'am.
Okay, yes, so it's the O2, the O3, and the 88 degrees.
Yes, ma'am.
Yes, absolutely, because that had to be on the same side. Thank you, Michelle. So that's basically what I was going on about earlier, guys, is please, I want you to be careful. The angle at the circumference, angle at the center, it needs to still be on the same side. So when I was pointing out to you earlier, if we go from A and D, we get the angle at the center, and from A and D, we also get an angle at the circumference. But it needs to be on the same side. So that is why Michelle was saying we've got to look at O reflex. Okay. So basically using things like vertically opposite angles gives me 88 degrees over here. Okay, interior angles of a triangle or adjacent angles on a straight line. It doesn't matter what you do. Over here, O3 would land up being, what, 92 degrees? Which means that that O reflex that Michelle was talking about, O reflex, is going to be equal to 88 plus 92 plus 88 degrees. And that means y is going to be half of that. So your 88 plus 92 plus 88, all divided by 2, and that's angle at center equals 2 times angle at circumference. Does everybody follow what we did there? And that's 134 degrees. Are we all happy with that? Okay, so that's quite hectic. When it's on the wrong side, you have to use the right side of the angle at the center to make sure that you're getting the right answer. Okay, guys, we have been going on for 55 minutes already, so we are going to take a short break. So that was theorem. Okay, thank you for coming back, grade 11s. It's theorem 2 that we've done. Now we're moving on to theorem 3. A very quick and short one. It kind of makes sense from what we just found out. We just found out that the angle at the center, which is basically that angle over there in this situation, is equal to 2 times the angle at the circumference. Since this is a straight line, that must be 180, so that must be 90 degrees. They refer to this reason as angle in a semicircle because this will only happen when you've got a diameter, because remember that would have to be an angle at the center. So if we've got a straight line going through the center from one side to the other side, it is the diameter. Okay, so that is what I was saying earlier with that first theorem. When is it useful that you've got a diameter? If you know that that's a diameter, you know that the angle subtended by that angle, so it's sort of carried, that angle over there that's held up at the circumference or subtended by the diameter is always going to be 90 degrees. And your reason is angle in a center, angle in a semicircle. And it's from the theorem that we've just done. Okay, so that's a quick and easy one. This is also something that we use to prove that something's a diameter. Now, that's probably one of the hardest concepts that they ask you with this, is they prove that something is a diameter or prove it is a tangent. So this is used to prove a diameter. So if they asked you to prove that something's a diameter, if this is a 90-degree angle, then that line must be a diameter. So it's like the converse, okay? And the reason they use is chord subtends 90 degrees. So this chord AC, they call it a chord because we're proving that it's a diameter. So at this point, we don't know. That chord is holding up a 90-degree angle. If I go from each end, so I put my fingers on the A and on the C, put my fingers there and I go to the circumference, that's subtending it at the circumference. And because it's a 90-degree angle, it must be a diameter. Okay, so that's what you'd be using if you're trying to prove it's a diameter. If you know it's a diameter, you use the other reason. Okay. So let's have a look at some examples now. Now remember what we've got. We know about the angle at the center and perpendicular and midpoints. We know the angle at the center is twice the angle at the circumference. So that's number 2. And we've got a third one. If we've got a diameter, we know it's going to hold up a 90-degree angle. So it is in circle O. So when they refer to a circle as being circle O, that is telling you that O is the center. Okay. So in circle O tells you that O is the center of the circle. So make sure you understand that language. So that's their way of saying that this is the center of the circle. So you need to know that. With diameter AC, so they've given us the diameter AC. DC is equal to AD. DC is equal to AD. Notice as I'm reading everything, I'm making sure it is clear on my diagram. B2 is 56 degrees. Determine the size of DAB. DAB, they're asking for the size of that angle over there. Okay, so I want you guys to all have a look at it. Think of ideas, remembering all the different things we've learned. At the moment, you can see there's no line from a center sort of going to a midpoint or perpendicular to a chord. So theorem 1 actually goes out of our mind when we see we don't have that. Okay, but we've got a diameter, so there's certain things that we should know are 90 degrees. We've got an angle at the center, and we can also go to the circumference from the same points. So those are the sorts of things that you should be using to try and figure out stuff. You don't need to give me the answer, but I'd like you guys to tell me what you do know about everything that you've read there. What do you know? Okay, so we know that angle D is 90 degrees because of angle in a semicircle. Absolutely. Okay, what else do we know? So we know that this is 90 degrees. I'm going to put it in my diagram, but in a different color because we've got to remember that we actually proved that. So I've been told that A1 and C1 will both be 45 degrees. Guys, this is an isosceles triangle. So we know that A1 will be equal to C1 because of angles opposite equal sides. Notice I'm doing this in two statements because you actually do need to do it that way. And that means that A1 is equal to C1 equal to 45 degrees interior angles of triangle. Sorry. Okay. Then Tristy said B1 is 34 degrees. Okay, here as well, remember we know that this whole thing is 90. Sorry. So we know that B1 must be 34, again, because of angle in a semicircle. Okay, angle B is 90 degrees. Yes, Bongeka, that's exactly right. So Shristi just went one step further and realized that that bit there is to be then 34 degrees. So we should be very close to what we need now. Now I'll show you what we're going to actually be using, because at the moment we've just been writing everything that we see, which is actually a dangerous approach, but at the moment, because we're teaching, like, I'm okay with doing it this way. Okay, we needed to use this 45 degrees because that's going to help us get there, but we only got that 45 because of those first two statements. So far we haven't used anything wrong. And B1, we need the 34, so we got that as well. Okay, C2 is equal to 56 degrees. Yes. Okay, but we can get there quicker, so I'm not going to write that down. So just letting you guys know what's going on with that thought process. As this is 56 degrees, because remember the radii are equal, so those must be equal to each other, which means we've got an isosceles triangle. And then using interior angles of a triangle, you could say that this is 68 degrees. Okay, but there is a quicker way of doing it, so I'm not going to write those down. Remember, we're trying to get to that red angle that I highlighted. Shristi said that A2 is 45 degrees. Co-interior angles. Okay, co-interior angles are only helpful if you've got parallel lines. I know the lines kind of look like they might be parallel, but if they haven't told you they're parallel, we can't assume it. Okay, so it isn't, but we're going to use a very similar statement or thought process that Michelle was using. Guys, remember all of these lines are radii. Okay, so see all those isosceles triangles we've got. There we go. Okay, so we can now say that A2 is also equal to 34 degrees. And here I can combine two reasons in one. Now I'm going to say angles opposite equal radii. You could actually leave out the word equal as well. And now that we got A2 and A1, therefore DAB is going to be the 45 plus the 34, which is what? 79. Yes, great. Well done, guys. That was amazing teamwork. Brilliant. Okay, so over here, we didn't even use the angle at center equals twice angle at circumference. We just used our 90-degree theorem. But always keep all the different things that you've got available to you in your mind. And that's one of the things that makes Euclidean geometry difficult. Okay, let's move on. Because we've only done 3 theorems, we need to get to 9. Okay, so there's the alternative diagram. So this is what I was talking about earlier, where the angle at the center equal to 2 times the angle at the circumference. You've got to realize the different ways, but I want to make sure we're all okay with that. So they look different. They don't always look, the nicest looking one looks like that, where you got the angle at the center, and it almost makes like a little teepee hut for the angle at the circumference. So that's the nicest looking one. It's very easy to spot, but these other ones aren't as easy to spot. Okay, so here do you see from A and B, I'm going to the center. If I put my fingers on A and B again, I can also go from those 2 points to the circumference. So that's why it's 2A at the center and A at the circumference. Looking at the next one, if I put my fingers on A and B, I can create an angle at the center, and putting on A and B again, we can go to the circumference. So the reason why they're showing you the different diagrams, guys, is because Euclidean geometry is visual. So you kind of need to see it. Okay. But you've got different techniques that can help you. So putting my fingers on A and B, it takes me to the center. But this is the one that we saw just now. But on A and B again, it also takes me to the circumference over here. But the angle at the circumference is on top of the vertex. So please make sure that the angle at the center you use is also on top of the vertex. So it's got to be in the same position. Do you see these ones? It's underneath, and the circumference ones were also underneath the vertex. I hope my description of the position makes sense. Okay, so those were the alternative diagrams. Okay, angles in the same segment. So this is now getting us to theorem 4. Okay, so angles in the same segment. Remember I spoke earlier about the word segment. It basically means if I were to draw a chord, RT. Remember I had 2 segments. The segments are the bits that chord, you know, like if I were to cut along RT, I create 2 pieces of a circle. And those pieces are called segments, okay? So I could almost color them in, but it's not. So that's the one segment there on that side of RT, and the other segment is on the other side of RT. Okay, so those are the 2 segments. So when they talk about angles being in the same segment, it means, again, I'm putting my fingers on each side of my chord, and I'm going to the circumference. But I could go anywhere in the circumference. If I'm coming from the same chord and going in the same direction, so the same segment, so both of the sections are going into my green section that I've highlighted, then those angles will be equal to each other. Okay. And the way we prove it is, you can see they've drawn the angle at the center. And that's literally how we prove it. Because remember, using my angle at the center rule, putting my fingers on R and T, I can create this angle at the center. And that angle at the center is going to be 2 times the angle at the circumference. But I've actually got 2 options for an angle at the circumference. So that means that those angles must be equal to each other. Angle P and angle M must be equal to each other. So that's how you do this proof. So again, we'll have a look at the proof. First thing you need to learn is you learn your construction. So you're going to draw in radii again. Learn your construction. Once you've learned your construction, learn what you have to do to try and prove it. So I would probably learn the reason that we use. We're going to use that whole technique of angle at the center. And that's what proves that our angles are going to be equal. Okay. So now we know that that's true. We don't have to go through this proof every single time. And we can just use this reason, angle in the same segment. Okay, there's different spin-offs of these. So the spin-off is kind of like your favorite TV program. When they finally end the season, they sometimes create another series that's got some of the same characters. It's like a spin-off. Okay, that's what a corollary is, really. So here it's saying if you've got equal chords, and this is actually something I think it was Shristi who asked earlier. No, it was Savannah. If my chords are always going to be equal or not, and your chords aren't necessarily equal, but if they are equal, they will create equal angles at that circumference. Okay, so this is saying that if they are equal, they will create equal angles. And the reason we use for that is equal chords, equal angles. Okay, here again, if we've got equal chords, they would also create equal angles at the center. Exactly the same reason, equal chords, equal angles. And then the last one is if you've got two different circles. But if the circles are the same size and they've got equal chords, then they also create equal angles. And again, you can just see it's equal chords, equal angles. So the circles have to be the same size, so they have the same size radii. And then we've also got the equal chords. So in this case, it would be angle G being equal to angle R. Remember, you go to the end point of the chord and you see where it creates the angle. The end points of the chord, and you follow your fingers to see where it creates the angle. Okay, and then going backwards, the converse. So this is something, if you know that okay, sorry. So before, let me go back. I actually want to go back all the way to the original theorem. Okay, so this situation here, we have 4 points on our circumference, on our circle. Okay, if I were to join all of those points, we create something called a cyclic quad. If we just talk about the 4 points that are on there, we talk about those 4 points being, the points are concyclic. Okay, so it's all this language. Okay, so we know what a quadrilateral is. It's something with 4 sides. Okay, so the cyclic quadrilateral means it's possible to draw a circle around it that goes through each one of those points. That's what the cyclic quad is. That's what the blue bit is. Okay, the 4 points are on their own is something that we just call points being concyclic if they all lie on the same circle. Another time we use a similar concept is if we talk about points being, I can't think of the word now, when they all lie on a straight line. Okay, and we sometimes have to prove that all 3 points lie in the same line when we use our gradients. Thanks, guys. Collinear. Okay, the 3 points, it's the same sort of idea. So concyclic, collinear. Okay, concyclic means they all lie in the same circle. Collinear means they all lie on the same line. Okay, so when we're just talking about the points, we talk about being concyclic. But if it is actually a 4-sided shape, we often call it a cyclic quadrilateral. Okay, so now if they ask you to prove, so this is if you're being required to prove that something is concyclic. If we've got 4 points and they want you to prove they're concyclic, or if you've got a 4-sided shape and you want to prove that it's a cyclic quadrilateral, you're going to use the converse of this. Okay, so again, we will get to examples with it. So let's have a look here. So here you can see I don't have a circle at all. And if I wanted to prove that Y, W, U, Z, if I want to prove that those points are concyclic, okay, so we can either prove concyclic or we can prove that if it was a complete quadrilateral, we'd be proving a cyclic quad. Basically, what we need to show them is that those two angles, you can see the X's are there. We would have to show them that those two angles are equal. I call it the bow tie theorem because you can actually picture it like it does. It crosses over like a bow tie. The top points of your bow tie have to be equal. The bottom points of your bow tie have to be equal. You don't have to prove both. You just have to prove either the tops or the bottoms. But if you get that right, then it means that the points are concyclic and the quadrilateral is cyclic. Okay, so this is often if they ask you to prove that it's cyclic and you say line subtends equal angles. Okay, so it's focusing on those angles being equal. So the only thing that changes is the reason that you're using, which does get confusing, I know. Okay, so here let's have a look at this first example. So it says given circle center O. The minute they've given you a center, guys, please remember they've given you the center for a reason. So you can start thinking of everything you know about the center of a circle. Our first theorem, if we have a line from the center to the midpoint or perpendicular, it tells us about the circle. But if you have a look at this center here, all the lines going from that center, they're not going to the middle or to a perpendicular. So I throw that theorem away. I don't have to think about it. The other thing is the angle at the center is equal to 2 times the angle at the circumference. So angle at the center equals 2 times angle at the circumference. That is something we've got to think about. Angle at center. I'm not going to write out the whole thing. So look at, see where I could possibly use angle at center. Okay. The next theorem we learned about the center was if we had a diameter. Okay, so if it went all the way across, but I don't have a diameter because we know that diameter, remember, subtends a 90-degree angle. So this is the only theorem that's going to help me with that center. Okay, think about that stuff before you get to the question, because half the time it answers your question before you've even got there. Okay, the next piece of information they've given me is that C is equal to 36 degrees. So I go here and I fill in my 36 degrees so that I know that it's on the diagram. Okay, calculate the values of the angles O1, A, and B. So now you guys are all on point. You guys have to help me. So either you're going to unmute and help me, or you're going to be typing in the chat, guys, and keeping me going. Because if I do all the work, then I'll be asleep in 5 minutes. Okay, so O1 is where we're going to start because it's the first one they asked for. Okay, so any ideas of how we could get to O1? We've only really got one new theorem that we could possibly use. But don't forget your old theorems. Don't forget about your triangles and parallel lines and stuff that you learned in grade 8, 9, and 10, please. Okay, so let's just see how we could make O1. I know the angle at the center equals twice angle at the circumference. I have to be able to put my point fingers on 2 different places on my circumference and follow lines to the center. Then I'd have to go back to those 2 points and follow lines again to my circumference. Is it possible to do that? That's the only way I can use this theorem. So I start off and I go to O1. And then there's actually quite a few places I could go. I can go up here. And the reason I'm going up here is because that's the information they gave me. So yes, O1 is 72 degrees. Well done, guys. Okay, so remember, angle at center, so that is O1, is equal to 2 times the angle at the circumference, which is 36 degrees. So if you just substitute into your reason, you will not make mistakes. So angle at center equals 2 times angle at circumference. And that means that O1 is equal to 72 degrees. The minute you've got an answer, guys, please remember, you go back to your diagram and you fill it in, because you might need it later. Okay, then they wanted angle A and angle B. So I've already had somebody saying that angle B is going to be equal to 36 degrees. There's 2 reasons we can use there. Okay, we can either use the angle at center theorem again, or I'm going to highlight the bow tie, and I'm specifically highlighting the bow tie. Why? Because you guys need to get used to this one. Okay, so you could have used angle at the center, because we've got the center angle now. But do you see my pretty pink bow tie? So that means the angle at C and the angle at B, so the 2 points on the side there, they have to be equal to each other. So that tells me that angle B is 36 degrees. Your reason for that is angles in the same segment. Okay, it was neater when it was a bit thicker, so I'm going to make it a bit thicker. And then we can do the same with B. Okay, so I'm going to then make a green bow tie. Do you see that angle A is also going to be 36 degrees? The same reason. You can also still use angle at center equals twice angle at circumference, but I'm trying to get us to practice this new theorem. And I want to make sure that you guys are okay with it. Okay, are we all happy? I always tell my class, if you're happy in your note, clap your hands. Okay, I've got a thumbs up. That'll work. Okay, let's have a look at what we've got next. Example 2. So this definitely looks a little bit scarier. It says, calculate circle ABCD with AB parallel to EF. Okay, I don't think that first word's supposed to be calculate. I think it's supposed to be given or consider or see or something. Okay, so they've given us the circle ABCD. Earlier I said when they talk about a circle O, it means that O is the center. Another way they refer to it is they'd use all the letters on the circumference. Okay, so that's another way they look at it. So I've got 4 points on the circumference. So straight away, we should be thinking of those 4 points we had earlier that created our bow tie theorem. Okay, very unmathematical term, I know, but look for those bow ties. We don't have the center of the circle, so I can't use any of my center theorems. I don't know if I've got diameters. I don't have the line from the center perpendicular or parallel, or to the midpoint. I don't have angle at center equals twice angle. I don't have the center of the circle. I can't use that. Okay, but I do have 4 points in the circumference, and at the moment, the only thing that we've learned so far is this bow tie. So the first thing it says is prove that CDEF is a cylindrical quad, also called a cyclic quad. Yes, a slightly different version of the name. Please don't make that make you panic. Okay, so we're having a look here. And they want us to prove that that one is cyclic. We know that the big one is cyclic because those points are on the circumference. They told us that. That was given to us. Okay. So they're wanting us to prove that the small one's cyclic. So our options are either proving those 2 angles equal, or proving these 2 angles equal, or those 2 angles equal, or these 2 angles equal. Okay, so any pair of those that I've done, so either the crosses, the colored in dots, the open dots or the dots with the extra dot inside, any pair of those, if we can prove those equal, then we know it's a cyclic quad. Okay, so now we know what our goal is to get our cyclic quad. We have to use that bow tie. What other information have they given us? They have given us parallel lines, which is definitely nothing that we sneeze about. We are quite happy to get parallel lines because the minute we see we've got parallel lines means we can use our fun angles. And in fact, it also means we can use our midpoint theorem from grade 10. Okay, those are the options we have for ourselves because we've got those parallel lines. Okay, so tell me what, with that information that I've just given you, knowing what we're trying to get, we're trying to get to some of the angles inside the little quadrilateral's bow tie. Okay, so look at those angles and see how I can use them and link them to the information that I know. And come up with some ideas. Okay, so I've got an idea of C1 being equal to F1. Let's have a look. C1 is equal to F1. We want to prove that, but we don't know if it's true yet because we don't know if this is a cyclic quad. So I'm going to highlight the bow tie that we've got, guys. We don't actually have, so this is the bow tie that I can use. Oh, sorry, I didn't need that last line. This is the bow tie. Oh, sorry, undo. There we go. Okay, so out of those, the angles that you gave me, I can use that bow tie because those are on a circle. But do you see F1 is not actually on a circle yet? So that's what we're actually trying to prove. We're trying to prove that C1 is equal to F1, but we don't know that. I know it feels like a silly little difference, so I hope you understand the difference. So this is the bow tie I could use. I can either use this blue bow tie or I can use this pink bow tie. Okay. I know for a very unmathematical term, I'm using it a lot. Okay, but we need to use those bow ties to link to that small quadrilateral. So if you look, let's start off all, but between the blue and the pink ones, do either the blue or the pink bow tie also connect to the small bow ties in the middle? And if they do, then that's the bow tie we're going to use. So do you think we need to use the blue bow tie or do we need to use the pink bow tie? Start off with that. And I hope that makes sense. So do you see here the pink bow tie is using these angles? And do you see that none of those pink angles that I've just indicated are completely inside my small quadrilateral? Okay, none of them are completely inside. So we don't want to use the pink. Yes, Benanti, perfect. We want to use the blue bow tie. Okay, and then I've got a suggestion. Angle D1 is equal to C2. Okay, again, be careful. Guys, we're trying to, and it's just one word, this word prove. Okay, that small quadrilateral, that pink one that I've highlighted there. Guys, that pink quadrilateral that I've highlighted, we don't know if it is cyclic. Do you see there isn't a circle around it? My bow tie theorem that we learned specifically needs a circle around it for those angles to be equal. So I cannot use that pink quadrilateral and say that those angles are going to be equal because there's no circle going through the points. Do you see? I have to use the big one. Okay, I hope that makes sense because I possibly should have started with question B. I think it would have made it easier. Okay, so we've decided we're going to use the blue one because do you notice that the blue bow tie if I look at those angles, do you see that some of those angles are actually inside the small cyclic quad? Okay, so if I were to draw a bow tie inside the small cyclic quad, do you see that C1 and D2 are angles inside the small cyclic quad? Okay, so that's where our starting point is, because that's where the two concepts overlap. So we're either going to look at C1 or D2. And I see I've got one suggestion that C1 is going to be equal to B1. Okay, using my blue bow tie. C1 is equal to B1. And that is angles in the same segment. Okay, now I need to somehow link, I need to eventually get to this angle here because that's my goal. If I started with C1, I want to show that it's going to be equal to F1. So from C1 equal to B1, what could B1 also be equal to? What other angles would B1 also be equal to? So we've used the bow tie. So we've used this first concept that they told us about circle ABCD. Remember they've also given us parallel lines. So what else would B1 be equal to? B1 would also be equal to F1. Okay, and this is why I don't like you guys highlighting, because you can't always undo everything that you've highlighted. Okay, but I can. So I'm going to make sure that everybody sees it. Okay, do you see here? There's my parallel lines. I've got a fun angle, an F angle. Okay, so that tells me that B1 is also going to be equal to F1, and the reason is corresponding angles, EF parallel to AB. Okay. Yes, A2 is equal to E2, but remember where we started? Because we started with C1, we're trying to get things that are equal to C1 eventually. So I went from C1 to B1, from B1 to F1. And if I look at all of those, what conclusion can I make about that? What conclusion can I make about that? Okay, so we've got that C1 is equal to B1, but B1 is also equal to F1. So what conclusion? C1 these two guys have to be equal to each other because they're both equal to B1. So therefore, C1 is equal to F1. We have now managed to prove. We proved it. We did not use a theorem that we couldn't use. We proved that those two guys are equal. Okay, because remember, we didn't know that there was a circle there. We couldn't assume that it was cyclic. So we had to prove that it is. So if those two angles are equal, it means that that quadrilateral must be cyclic. It's kind of going backwards. Okay, so then we say, therefore, CDEF is cyclic. And make sure you use the correct reason. Lines subtends equal angles. A lot of people say converse of angles in a cyclic quad. As long as you put in that word converse, they do accept that as well. Okay, so I know working backwards is hectic. But now that we know that this is cyclic, I've just proven it. Notice nowhere in my proof do I talk about it being cyclic. I only talk about it being cyclic in my conclusion. You cannot use the cyclic quad before then. Okay, now that I know it's cyclic, whether you manage to answer that first question or not, remember it for the next question. because if you've managed to prove it, or if you haven't, you now know from the second question you can assume that it is cyclic. Okay, so they said D2 is equal to 38 degrees. So now we've got two cyclic quads here, even though we don't have the circles. D2 is 38 degrees. Calculate E2. What would E2 be? Now remember, we've basically just proven that it is possible to draw a circle around here. So you do have a bow tie in the small quad and in the big quad. So what would E2 be equal to? Yes, 38 degrees. Brilliant. Brilliant, Zanel. Yes. Okay, so we can now say that E2 is equal to 38 degrees, and that is going to be angles in the same segment. I've written that very untidily. Okay, because now we know it's cyclic. I hope you guys, let me just highlight the bow tie so that you guys can all see that bow tie here. And the only reason why I can use the bow tie for the small shape now is because we've just proven it's a cyclic quadrilateral. So you either have to have the circle going through all the points already, or you have to have proven it using other methods first. Okay, I hope that makes sense. Proving the cyclic quads and going backwards is actually probably one of the hardest concepts. Okay. And there's the answers. Okay, opposite angles of a cyclic quad. So here again, we're assuming that it is a cyclic quad. You can see all 4 points are on it. What's nice about the opposite angles of a cyclic quad are they supplementary. Okay, so basically what they're trying to tell us here is that those two angles, Q plus A, would be equal to 180 degrees. It'll also be the whole of angle D plus the whole of angle U. D plus U would also be 180 degrees. The opposite angles will add up to 180. Okay, and that makes all of them add up to 360, which is true for every quadrilateral. All of them will always add up to 360, but only as it's cyclic will the opposite ones add up to 180, only when it's cyclic. Okay, so they've got the proof of the theorem again for you. Okay, and again, you're going to learn your construction and you're going to learn what method you use to prove it. You're not going to try and learn every line off by heart. Let's see if we can have a look at how we're going to use this. It says calculate the value of alpha. Now we've got 4 points on a circle, so we know we've got a cyclic quadrilateral. The only two theorems we've got with us 4 points is our bow tie, which you can see the bow tie isn't drawn here. Okay, you can see there's no bow tie actually drawn. Yes, you can draw it in, but it's not actually drawn. So we're not going to use the bow tie theorem. The only other thing we've got for those 4 points is that the opposite angles add up to 180. So what can we say if we look at this? The only thing we've learned is we've got opposite angles are supplementary. Remember, supplementary means it adds up to 180, like a very supple person can do the splits, okay, like a straight line. So the opposite angles, and then we've got our bow tie. I'm not going to write bow tie. I'll draw it. We've got our bow tie, which is angles in the same segment, but straight away I'm putting a line through that because you can see there's no bow tie in our diagram. So what can I say about the angles in this diagram? Okay, so a whole lot of you, some of you have solved it and that's fine. Some of you typed it in as the equation, but yes, these opposite angles will add up to 180. So angle Q plus angle A is 180 degrees, and that is opposite angles of a cyclic quad. We can't say just of a quad because it only happens when it's cyclic, which means you've got 55 minus alpha plus 41 degrees plus 3 alpha equals to 180 degrees. And then you solve it like a normal equation from there. And I would like you all to solve it, but we've got an answer of 42. I want to see if you guys agree. Okay, Bongeka definitely agrees. Also gets 42 degrees. So does Shristi, brilliant. Okay, make sure you can do your algebra. Every single time we practice the algebra, guys, I need you to practice it as well. Okay, so do you see those opposite angles had to add up to 180, and then it is just algebra. Brilliant, great. Let's see if we've got another example. Okay, so here they're just asking us, so I just want us to discuss it, and then we're going to take another short break to make sure that we all stay awake. Okay, is the quadrilateral a cyclic quad? Okay, so they've got GLJM. So let's ask with that one first. And you're going to tell me whether you think GLJM, so GLJM, they want to know if that's a cyclic quad. So let's see what they've told us. They've said given circle GHJK. So they've told us that those points, these points here, they've told us they're on the circle. They said that GM is perpendicular to HJ. GM is perpendicular, so that one there is 90 degrees. GL is perpendicular to LJ. That one there is 90 degrees. And that highlighted thing that I've just highlighted, do you guys think it's a cyclic quad? Yes or no? Okay, so some of you are still focusing on the fact that you can't see the circle. Guys, something can be cyclic even though the circle hasn't been drawn in. So you've got to think about what does it have to be for it to be cyclic. And what we need for cyclic, we either need our bow tie, where those angles are equal, or we need a situation where those opposite angles add up to 180 degrees. Okay, you don't have to see the circle. So yes, the circle itself at the moment does not tell me that it's cyclic, but all of you who said yes, do you see that that's a 90 plus a 90, they are going to add up to 180. The opposite angles are supplementary. So yes, this is going to be cyclic. Okay, so you don't have to see the circle. Let's look at the next one. It says GLJH, and they want to know, do you think that one is GLJH? Do you think that one is going to be cyclic? Remember what you actually need for it to be cyclic. Yes or no? Do you think the pink one is going to be cyclic? Okay, well done, guys. That one's definitely a no, because this angle, H, is definitely not 90 degrees. And for my opposite angles to be supplementary, it's going to have to be 90, because here we'd need a 90 degrees plus another 90 degrees. But at the moment, we've got 90 degrees plus an acute angle. Plus an acute angle. So that is definitely not equal to 180 degrees. So no, that would not be cyclic. Awesome. Okay. Guys, we're going to take another 10-minute break. It feels like we're flying through this. I hope you guys are having as much fun as I am. Probably not. Okay, that's okay. Okay, guys, so let's take another 10-minute break. Great, thank you. Okay, so let's have a look at Theorem 5. Guys, we've been doing so much work here, so let's have a look. So Theorem 5, example, oh, sorry, we've already done Theorem 5, example 2. Okay, we did this example earlier. Okay, so guys, from my experience with our last example, I'm going to fly through the converses with you, but I think our focus needs to be on the basics for today. So I'm going to actually avoid those examples where we go backwards. So, you know, earlier when we proved that something was a cyclic quad. But here, this is another way to prove that something's a cyclic quad. So you can either use your bow tie method, okay, where we prove that the angles at the top of the bow ties or the angles at the bottom are equal. Okay, but another thing, if you've got a quadrilateral and you're able to prove or show that those opposite angles do add up to 180, then that means that that quadrilateral must be cyclic, or that the points are concyclic. So again, you don't need to see the circle. You can see this time they've actually drawn a dotted circle around. So the circle doesn't have to actually be there for it to be a cyclic quad. But if any of the cyclic quad rules do apply, then it means it's possible to draw that circle around it, even though you can't see it. Okay. And then here you can see they've left out the word cyclic. That's basically the difference in the reason. And they say opposite angles of quad are supplementary. But we're not going to do examples of those because I feel like they're actually working backwards when you're just learning the geometry is very hectic. Okay, so the exterior angle of the cyclic quad, if you have a look here, we've got a quadrilateral, and I want to focus on what we're actually talking about when we talk about an exterior angle. Okay, an exterior angle isn't any random angle on the outside. Okay, it's a specific type of angle on the outside. So for something to be an exterior angle, you have to take the side of the shape and carry on straight. Okay, and that creates an exterior angle with one of the other sides. So for example, if I were to draw this line over here, do you see that that's not going to create an exterior angle because this side carries on that direction, that side carries on that direction. Neither of them overlap my pink line. Okay, so you have to actually extend one of the sides of the shape. It's the same with the exterior angle of a triangle. So you have to extend one of the sides, and that creates what we call an exterior angle. It's not just any angle on the outside. And that exterior angle is equal to the interior opposite. Okay, so from where that angle is, you go inside, and then you go directly opposite. And that is how you find out which angle it's going to be equal to. And always think of that, because you don't want to land up saying that this guy here is X, the U isn't X, the D isn't X. You go where your exterior angle is, you go inside the quadrilateral, and then you go to the opposite angle, and that's the one that is going to be equal to X. And that reason is the exterior angle of a cyclic quad. Okay, again, you can use that to prove that something's a cyclic quad, and if you've managed to show that those are both equal to each other, then it has to be cyclic. So if they ask you to prove a cyclic quad, you're doing that converse. Okay, so let's have a look here. GFE is a double chord, and H1 is 75 degrees. Okay, so make sure we understand what the story is that they've given us. All that it means for it to be a double chord is that this chord here belongs to both of the circles. So they're kind of telling you that the point C and that the point F lies on both of the circles. That's all they're telling you. And then H1 is 75 degrees. So we're going to write the 75 degrees there. Okay. So if we have a look at everything we've learned today, we learned stuff about the center of a circle. Okay, but do you see in this diagram, I don't have any centers. So all those theorems about the center of the circle, you can forget about momentarily. Okay, so that's one of the processes you need to follow to help you figure out what you're going to use in a test. Because remember, a test takes all of these theorems and mixes them all up. Okay, so we don't have anything of the centers. Then we learned if we've got 4 points on the circle and they create a bow tie, then we've got angles in the same segment. We also learned that if we've got 4 points, the opposite angles are going to add up to 180. And lastly, we learned that the exterior angle is equal to the interior angle. That we do have. We do have the 4 points on both of these circles. So we do have cyclic quadrilaterals. Okay, but again, we can eliminate that one because we do not have a bow tie. Okay, so we know we're either using opposite angles of a cyclic quad or the exterior angle of a cyclic quad. Okay, so now that we've narrowed it down, it helps us to start looking at what they're actually asking for. So Zanel's already chucked out an answer. Let's have a look. So they said determine the value of D. So this is where we're trying to get at. But at the moment, the only information we have is about H1. So guys, nudge, nudge, wink, wink. If you only know H1, you start with H1. Okay. So Zanel told me that H2 was going to be 105 degrees. Absolutely correct. Why is that going to be 105? That's 105 because of adjacent angles on a straight line. Okay. Then we've got Bongeka says that F1 is 75 degrees. Okay, so F1 is 75, and there's two ways you could have got there. I'm going to do it the quicker way. So I'm going to write that one down, and I'm going to do it the quicker way. That is because of an exterior angle of the cyclic quad. Okay. If, however, you started with the same place Zanel did, with 105 degrees, you would make that statement first. So you would have done that. There's nothing wrong with it. You would get there. You would have first said that H2 is equal to 105 using adjacent angles. Okay, I'm not going to write that all out. Then you would have said F1 equals 75, but this time your reason would have been opposite angles of the cyclic quad. So it just means you have to follow both steps. But guys, if you do that, you have to write down both steps. You can't just write down the last step because then you don't get any of the marks. So please realize every step that you use to get where you are going must be written down with a reason. Okay, so we've got F1 is equal to 75 degrees. And then I don't want to miss anybody's comments out. So Michelle said H1 is 75, therefore F1 is 75 straight away, yes. Zanel says F2 is 105, exterior angle of a cyclic quad, absolutely. And then you can go D because of opposite angles of a cyclic quad. But from the 75, we can actually just go straight into saying that angle D is also 75 degrees exterior angle. So we can just use that one twice, and that just gives us 2 steps in total to get to D. Okay, but guys, it's okay if you did extra steps. Just remember every step that you've used to get there has to be correct with the statement and the reason. Okay, so for example, if I were to allocate marks to this, I'd probably give 1 mark for the statement, 1 mark for the reason. And because the next one's exactly the same reason, that one you would need the statement and reason correct. So you'd get 3 marks. If you do those extra steps, you need all of that to be correct to be able to get those marks. Okay, the statement and the reason for every single step for you to be able to get those marks. So just be aware of that. That's why we prefer finding the quicker way, but it really doesn't matter. Okay, let's carry on. Bokamoso, do you have a question? No. Okay, example 2. Here they're going to ask us to prove that something's a cyclic quad. Guys, the solution is there. If I've got time, I'll go back to it. But I think right now we actually need to focus using the theorems forwards before we start using them backwards. Okay, so I'm going to click so we can have a look at it. But basically you can see they haven't used any of our quadrilateral theorems, but they've managed to prove, using everything else they know about geometry, they've managed to prove that C1 is equal to F1. So because those two are equal, and this is the exterior angle of a quad, it means it must be cyclic. So the word cyclic only comes in that final statement. Okay, Next theorem, tangent perpendicular to radius. Now I've just remembered that I didn't actually discuss tangent with you. A tangent is a line that literally just touches the circle in one point. So if it crosses over completely, that is not a tangent, okay? But if you touch it in one point, so it just touches the circle and carries on straight, that is what we call a tangent, okay? And if you've got a tangent and you've got a radius from the center, so it's kind of like a combined of the centers, those two things will always be perpendicular. So your radius, if your radius goes and touches the tangent at that point of contact, it's always going to be 90 degrees. And the reason we use for that, line perpendicular to radius. Oh, this is the converse. Did I skip something? I'm actually going to go back because that seems like an odd order. So I don't know if I landed up clicking too fast somewhere. Yes, I did land up clicking too fast somewhere. Okay, so tangent perpendicular to radius. There you've got a tangent, there you've got the radius. They will be 90 degrees every single time. And like they sometimes ask you to prove that something's cyclic, they sometimes ask you to prove that a line is a tangent. And that's what that converse was that we were just looking at. Okay. So over here, you know that they're 90 degrees, therefore this must be a tangent. Okay, it's working backwards, and then you can either say line segment perpendicular to radius, or you say converse of tan chord. Let's have a look at this first example. Given circle center O. So they have given us the center. The minute they have given us the center, you start thinking about everything you know about your center theorems. So what center theorems do we have? We've got the center, line from center, perpendicular, and midpoint. So have a look here. Do I have any lines going from that center to a chord that could be the midpoint or perpendicular to a chord? No, it's only going to this here, which isn't actually a chord. So that's my one center theorem immediately scratched. Then do I have an angle at the center that also goes to the circumference? So remember where you put your fingers on the 2 points on the circumference, and can you go to the center and then also go to the circumference from those points? Okay, you kind of do have that because you've got a diameter. So you definitely have that diameter theorem. The diameter theorem, which is angle in semicircle. Okay, so we've got that one, and that's the only information we actually get from that center. The next thing they said, with tangent ZYU. At this point, the only tangent theorem we've got is we know that our tangent is going to be perpendicular to any radius. Okay, so that's in our head now. We know the tangent has to be perpendicular to the radius. So that's what we're getting from the tangent. This is what we're getting from the center. Then what else have they told us? They said that MN is equal to FG. Okay, MN is equal to FG. So what's that telling me? The minute I know that I've got equal chords, remember, equal chords equal angles. Okay, so we've got equal chords equal angles. Okay, and then lastly they say H is equal to 18 degrees. So I'm going to fill that in my diagram. They want you to determine the size of Y2. Okay, guys, so do you see? I read the story and I analyzed everything that I could possibly use before I read the question. It helps narrow down your options. Otherwise, if you look at this picture, you could stare at it for hours and feel confused. But at least now you've got some ideas of what you could use. Okay, so we've already had some suggestions come through. Benati says that H is equal to Y1. So let's have a look here. H is equal to y1, that is using this theorem, equal chords, equal angles. Absolutely. So straight away I can say that y1 is going to be equal to 18 degrees, equal chords, equal angles. Okay, then Zanel said that y is equal to 18. Okay, be careful, Zanel. I know it might just be because you're typing. I think you forgot the y1. Okay, be careful. It's also not angles in the same segment. It's equal chords, equal angles. So your reason's wrong, but your concept is perfectly correct. It's the corollary. And then you carried on saying, because we know this guy is perpendicular, so now I'm going to just use the colors for what we analyzed earlier. That means that y2 would have to be 72 degrees because of our tangent being perpendicular to our radius. Okay. Okay, so please make sure all of the, and it's a lot to remember, especially since you've been learning this in like the space of 2 hours, guys. So I'm sure this is overwhelming on a big degree, but that's why I'm trying to break it down with you, and I hope that it's helping. Okay, and I know some of you have done this before, and I think you might be flying through it and think that it's all boring, but for the rest of you, I hope you're managing to keep up. You guys have been absolutely amazing. Okay, I'm going to clear all drawings. Let's see what we've got next. Okay, they've said here, prove that it's a tangent. As I said just now, definitely, I think if this is our first lesson on this, trying to go backwards is actually quite hectic. Okay, so I'm not going to put a lot of detail on this, but we will make sure we understand. So proving that it's a tangent, you're not going to use any of your tangent theorems in your proof, except you're trying to prove the things that you know. So the only thing we know about a tangent, if that guy's a tangent, this one has to be 90 degrees. So I have to try and prove that it's going to be 90 degrees, okay, without using my tangent theorems, because that's what I need to prove. Okay, so that's the concept of working backwards. And you can see here they've used all the information they've given us, 8 centimeters, 17 centimeters, 15 centimeters. Yes, absolutely, Benati, brilliant. And you can see they've used Pythagoras, and they've shown that Pythagoras is actually going to work. So they've done the calculations separately. They took the longest side and squared it. Then they took the two shorter sides, squared them and added them up. Notice that they're different calculations. Okay, they're different calculations. Because they got the same answer, they know that this is true, which means that there must be a 90-degree angle because of Pythagoras' theorem, the backwards of Pythagoras' theorem. Okay, and then this is the first time that they mention the word tangent in their conclusion. They have not used the tangent theorems at all before that. Okay, and that's the concept of proving a tangent or proving a cyclic quad. Okay. So here's another tangent theorem. I think it's our second last one. Okay. So here we've got two tangents, and they call them tangents from the same point. So if you'll end up having two tangents drawn from one specific point, from that point to where it touches the circle, those sides will land up being equal to each other. Okay, so these sides here will always be equal. So you'll find often, and sometimes they don't even draw it in for you, do you see that creates a nice little isosceles triangle? So that's often how they connect this concept, where they use the isosceles triangle. So you would need to realize that those sides are equal so that you can use the triangle concept as well. Okay, so they have given us the proof of this theorem as we've discussed already. Guys, I don't want you to be trying to learn these proofs off by heart. You're going to mess it up. So you focus on the construction. So you're going to construct the radii. So remember what your construction is. And then how do you go about the proof? So we're going to use congruency, RHS. Okay, so the construction and the method, focus on that. If you still get stuck on trying to do it, then please add more to the method. So talk about the radii and the fact that you've got a common side, or which two triangles you're going to prove congruent. Okay, that is how you're going to study these theorem proofs, because then they're going to be nice, easy marks. Okay, so that's tangents from the same point. So let's have a look at our example. It says PK and KN are tangents. So the minute you see the word tangents, everything that we've learned about tangents so far. So for tangents so far, we've learned that the tangent is going to be perpendicular to the radius, and we've learned about tangents from the same point. So we go to our diagram and we do have a radius there, so that could be useful. And we do have two tangents from the same point K. Okay, so that could be useful. So we could use both of them. So I'm going to remember both of them. And that's from the word tangents. Then they tell us the circle center are tangents to circle center M. So we know that we've got the center of the circle. So let's think about everything we know about the centers of the circle. We've got three theorems, okay? The angle from the center, the line from the center, does it go to a chord anywhere? Okay, yes, it does go to this chord here, PN. Okay, is it the midpoint or is it perpendicular? At this point, I don't know. So yes, maybe it's going to be useful, but at the moment, I'm not ready to use it yet. Okay, other center theorem, angle from center equal to 2 times angle at circumference. So can I put my fingers on the circumference and go to the center and go to the same 2 points and go somewhere to the circumference? No, I can't. So I'm not going to use that. Okay, and the last center theorem is if I've got a diameter. I don't have a diameter. So at the moment, the only thing that's useful for the center is the fact that that helped us with the tangent and the radius. Okay, that's what told us that this was definitely a radius. Okay, if N1 is equal to 24, so you fill that in, N1 is 24 degrees, determine the size of PKN. They want the size of that angle over there. Okay, so we've gone through all the theorems we know, and we've got two that we could use, tangent perpendicular to radius or tangents from the same point. So I am now ready for our ideas. We've analyzed it. We know what theorems we can use. What ideas do we have here? Okay, N2 is 66 degrees. Yes, Michelle. Brilliant. N2 is going to be 66 degrees. Why? Because our tangent has to be perpendicular to the radius. That has to be 90 degrees. So I'm going to fill that in, 66 degrees. Okay, I see a bow tie. Guys, well done. There's definitely a bow tie, but please remember your bow tie, and I'm going to quickly highlight it. The bow tie is definitely there. But the bow tie is only valid if all of those points are on the circumference of the circle. Okay, and you see only 2 of those points are on the circumference. The other 2 points are not. So be very careful, because that is a big trap. Is you see the bow tie and you want to use it, but those bow tie points have to be concyclic. They have to be in a circle if we want to use them as our bow tie. Or if we're going to prove that they're equal to make it a cyclic quad. Okay, but because it's not in the quadrilateral, we can't use the bow tie. Okay, so we got the 66 degrees. We've used the tangent perpendicular to the radius. Okay, what else could we use here? Okay, so N2 is 66 degrees. We've used the tangent perpendicular to the radius. I said that there's one more we can use, the tangents from the same point. It's the newest one we've learned. What's special about two tangents from the same point? Are you guys still with me? Are we that tired? We're nearly at the end. They are equal in length. Thank you, Benati. If you guys are tired of typing, you can always unmute. Hey, I would love to hear your voices. Okay, so we've got that PK is going to be equal to KN. And I'm going to show you that on the diagram because that's what we're writing down. And the reason is from tangents from the same point. Okay, so if those are tangents from the same point are equal, I've now created, look at this very special thing that we've created, an isosceles triangle. Okay, so I've been focusing today on our new theorems. Please don't forget what you've learned in grade 8 and grade 9 and grade 10. Okay, so why is the isosceles triangle going to be so special? Yes, Bongeka, thank you. Yes, Shristi. Okay, this angle here at P, NPK, is also going to be 60 degrees. Why? Because of angles opposite equal sides. Okay, so now we've got that this is 66 degrees, which can finally get me to my goal. So thank you, Michelle. Yes, angle K is going to be 48 degrees because of interior angles of triangle. Please make sure you do still include this step of NPK. Okay, every step that got you to the fact that this is 48 has to be included. As much as you already see that, oh, that's going to be 66, which means that's 48. If you don't make those statements, you are going to lose marks. Okay, I hope that was all good. I'm about to clear. And let's see what we've got up next. Okay, so they're giving us our answers here that we've already got. Okay, this is our very last one. Okay, this is theorem 9. It's also got to do with the tangent. I call this one the surfer dude. Okay, because I find that generally when I teach it, people struggle to figure out which angle is going to be equal to which part of the diagram. So I use a surfer dude to try and explain it, and I hope it helps you guys. If it doesn't help you, forget about my surfer dude, and if you know how to find the angle, then great. Okay, so I call this my surfer dude theorem, and it's basically when you've got a tangent creating an angle with a chord. Okay, so we've done the tangent and the radius. Okay, so the radius is very special because it goes from the center. But now we've just got a chord. Okay, so there's a chord over here. And here's my tangent. The angle between the tangent and the chord is going to be equal to the interior opposite angle at the circumference. Okay, so the angle between the tangent and the chord is equal to the interior opposite angle at the circumference. If I went to the other side, the angle between this chord and that tangent is that angle there. If I go inside the opposite one at the circumference, it's that one over there. Okay, so when we apply it, I'm going to show you what I'm talking about when I'm talking about my surfer dude. Actually, no, I suppose I can show it to you now, but these other little lines make it a little bit confusing. Okay, so we're going to focus on the pink one. Okay, so whichever angle you're talking about, I'll show you my surfer dude. Whichever angle you're talking about between the tangent and the chord, that is where your surfer dude is standing. So when I'm talking about a surfer dude, I'm talking about the guy who's a windsurfer, not the surfer who's just on the board. It's the windsurfer. So he's got to hold on to a sail, and those sails are usually a triangle, right? Okay. So here's my surfer dude standing by this angle, and this is his sail, this triangle that he's got to hold on to. But do you see he's got to hold on to this side over here? Because that's where he's standing. So the side that he's holding on to, you go to the angle opposite. And the angle opposite is the one that's going to be equal. So those are the two equal angles. And that is my Surferdue theorem. Those are the ones that are going to be equal. So wherever he's standing, he holds onto the triangle where he's standing, and the angle opposite in that triangle is the one that's going to be equal. Okay, if my Surferdue was standing on the other side, because I've got lots of colors, we can make a big mess. Okay, he's going to hold on to this side of the triangle, and the angle opposite that side of the triangle is C2. So those are the two angles that would be equal to each other. C2 and A1. Okay, so that's why I call it the Surferdue, to help you try and imagine which angles are going to be equal. Let's just quickly run through the proof. This is one of the proofs you need to know. Okay, but again, as I've said before, you're going to focus on how to do the proof, not try and learn it off by heart. So the first thing you focus on is, what do I have to draw in? You have to draw in the diameter and then join the join the other end of the diameter to one of the points. Okay, so join DC. So you'd have to find a way to describe that so you remember. And then here is the proof. So what method am I going to use? Think about the theorems you have to use so that you know how you would go about it. And that is what you learn. Please don't try and learn every line off by heart. And now that I've said that 9 times today, I'm hoping that we're okay with how we would go about learning them. Okay, so let's have a look at this first example. It says TRN is a tangent at R. So the minute you see that you've got the word tangent, you start thinking about your tangent theorems. Okay, we've got 3 of them. Pretty much everything comes in sets of 3s. Okay, so we've got TRN. So if we've got TRN as a tangent and we know the center, then we've got the tangent perpendicular to the radius. But do you see I don't have a center? So I cross that one off my list. I'm not going to use tangent perpendicular to radius. Oops, sorry, radius is not going to be helpful. The next tangent theorem, I need 2 tangents. I need tangents from the same point. I've only got 1 tangent, so I cross that off my list. It's not going to be useful. The next tangent theorem is your tangent and your chord. Sorry, the angle between the tangent and the chord, the Surferdue, the one that we've just learnt. Okay, so that's the only information I can use for the tangent. What else have they said? SR is equal to RQ. So SR, oh, sorry, that's not SR. SR is equal to RQ. Okay, so what does that help me with? SR is equal to RQ. I've got equal chords. So that means I could possibly use equal chords, equal angles. Okay? Equal chords, equal angles I could use. It's also created an isosceles triangle. So we won't forget that we've got an isosceles triangle. That's all from the fact that SR is equal to RQ. Then they said R1 is equal to X. So we fill it in on our diagram. And find 5 angles equal to X is the question. Okay, now something that's on here, but they didn't say it in the story, which you must please remember, is, do you see I've got 4 points on my circle? So all of the things about our cyclic quadrilateral could also be useful. So let's think about the 3 things we know about a cyclic quad. The cyclic quad, we've got our bow tie, okay? Angles in the same segment. And I do have a bow tie drawn, so that one could be useful. That's the one cyclic quad. The next one is the exterior angle of a cyclic quad. Exterior angle. And I do have an exterior angle. Do you see that that side carries on and it goes past? So I do have an exterior angle. So that could also be useful. And the last cyclic quad one is that the opposite angles are supplementary. Opposite angles, supplementary. Okay, so there, that's kind of just from looking at all the information in my diagram, in the story. That's what's starting to buzz in my head, and now I'm going to try and use all that information to find as many angles equal to x as possible. Okay, that is the brainstorming that you should be doing, especially if you struggle when you look at the picture and you can't see anything. So what you can do is you don't have to brainstorm straight away. You'll find as you practice, you might see some of the things straight away and you can put them down. But when you get stuck, brainstorming is the way to go. So if you didn't find all 5 angles, brainstorm to see what you could possibly use. Okay, so I've already got some answers, possibly that x is equal to P1. So we shall see here x equal to P1, that is my surfer dude. So the angle between the tangent and the chord, my surfer dude is holding on to that side of the triangle. And do you see that is my opposite angle? So yes, x is going to be P1, or P1 is going to be equal to an x. So I can put my x over here. That's using my surfer dude. Actually, let me stick with the same color so you guys can remember what we did there. So that was the pink guy. Okay, so this guy is x. So we're going to say P1 is equal to x. And the reason is our tan chord theorem. Okay, then I've also been told that x is equal to P2. And that's using the equal chords, equal angles. Brilliant. Because P1 and P2 have to be equal to each other. Okay, we've got 2 angles equal to x. Guys, we need 5. It's okay if you don't find an x straight away, but you can tell me other stuff that you know in terms of x. Okay, we've used our tan chord. We've used equal angles, equal sides. The moment the isosceles triangle isn't helping me with anything in terms of x, so let's go to our red stuff here, our quadrilateral things. We've got bow ties. Okay, should I draw in our bow ties for us? Here's one bow tie. Okay, so I want us to focus on that bow tie before we carry on. Is that bow tie going to help me with anything being equal to x? S2 would be equal to x, guys. Remember, that's basically the tops of the bow ties. They are going to have to be equal to each other. Okay, so using our red, we know that that is going to be x, and we're going to say S2 is equal to x. And the reason for our bow tie, please don't write bow tie, is angles in the same segment. Okay, so S2 is equal to x. Brilliant. Okay, so I'm not going to draw the next bow tie for you guys. You guys can find the next bow tie, or you might not even use a bow tie. What else is going to be equal to x? Once we've finished finding our 5 angles equal to x, we're going to take a break. So the quicker you find it, the quicker we take a break. Q2. Okay, so Nicole, you said Q2 is equal to x. You're right, but I want to know what reason you used, because there's actually 2 different reasons at this point. So can you type in Nicole or unmute and tell me what reason you used for Q2 equal to x? Angle in the same segment. Okay, so you used the other bow tie, so that's fine. So we're going to keep it in red. So we're going to call this guy x here, and we're going to say that Q2 is equal to x, angles in the same segment. Okay, and that's just so everybody can see, that is using, no, I'm highlighting the wrong one. That is using this bow tie over here. Okay, that's how we got that x over there. So yes, absolutely. But you could have at this point said angles opposite equal sides. You could have used your isosceles triangle as well. You could have said angles. Let's put it underneath. I'm just letting you realize that sometimes there's a different reason. You get the same answer, angles opposite equal sides. You could have used that for your Q2 equal to X as well. Okay, that's perfectly fine. Okay, then we've got angles in the same segment, S3. Okay, let's have a look at how we could highlight with S3. Angles in the same segment is still our red. S3. S3 would be equal to R3. And unfortunately, I don't know if R3 is going to be equal to X. I don't have that. We've got Q2 equal to X. So unless I can get that R3 is equal to X, we're not going to be able to say S3 is equal to X. Okay. So what else? I'm going to give you a hint. Remember, my surfer dude could stand on either side of the tangent. Okay, so what happens if the surfer dude stood on the other side of the tangent by angle R4? R4 would be equal to, is it going to be equal to P1? Let's have a look. Okay, so if my surfer dude is standing over here by R4, he's holding on to that side. Okay, the angle opposite that is P2. Okay, yes, sorry, Benati, I see you've just corrected yourself. So R4 is going to be equal to P2, so therefore it must be equal to X, and that is our fifth one. R4 is also going to be equal to X, tan chord theorem. And it looks like there's a rainbow on my page. I hope that the colors have helped and not just confused things. Okay, but I used the colors so that you kind of know which theorems we're using. And you'll notice all that brainstorming we did. And guys, again, so you don't have to brainstorm at the beginning. I always brainstorm at the beginning because I know some children are getting stuck right from the beginning. If you see answers straight away, get the answers down. You don't have to brainstorm, it's fine. But the minute you get stuck, you need to be brainstorming. Okay, so we're going to have a look at some past paper questions and see if we can do it all together. Guys, I just want to stress, if you're feeling very overwhelmed today, you have been taught 9 new Euclidean geometry theorems. It is a lot, okay? So I will be walking you through, but I need you guys to listen and pay attention to the walkthrough so that you do have a concept of how to approach it, because only the practice will help you get used to all of these theorems that are now in your head. Okay, it does kind of fall under 3 different types of categories. If you've got the center, if you've got 4 points on the circle, which is your quadrilaterals, and if you've got a tangent. Okay, so there's only 3 different types of theorems, and then if you think about which ones you can use, it helps narrow it down when you actually hit the problem. So that is something that we're going to be focusing on as we look at these questions. So this is from your questions and memos. Okay, and you can see here in this first one, in the diagram below, O is the center of the circle. So they've told you about the center. So you start thinking about all your center theorems. And I'm going to summarize them quickly. I know you've got notes with summaries, but just little diagrams so that I can reference them while we're going through. Quadrilateral, A, B, C, O. So they've told you you've got a quad, but if you look at the diagram, it's not in a circle. So it's not cyclic. Okay. A and C are on the circumference. AB is a tangent, so they have also given you a tangent to the circle. And BC is a tangent to the circle at point C. D is the midpoint of a chord, so the midpoint of the chord leans towards that first one. They've given you 2 sides equal. E is the point on the circumference. Okay, so let's just have a look quickly at all the theorems that we could possibly use so that I can reference them throughout our discussions, I'll just slide backwards and forwards because it's easier than me having to draw them every single time. Okay, so first of all, we've got our center. Okay, so our center theorems, you've got the one center theorem where you've got a chord and either the perpendiculars or the midpoints. Okay, then you've got the next center theorem, which tells me if I've got an angle at the center, it's equal to 2 times the angle at the circumference. Okay, and then the last center theorem is if I've got a full diameter, I know it's going to create a 90-degree angle. Those are our center theorems. Then we've got our quadrilateral theorems, our cyclic quadrilateral theorems. My first one is my favorite bow tie. Okay, remember the tips of the bow ties on the same side are equal. It has to be on the same side. That's why they call it angles in the same segment. Then we also know that if we've got a cyclic quadrilateral, that the opposite angles are going to add up to 180 degrees. And then lastly, we've got the exterior angle, and please make sure you remember it's not any angle on the outside. One of the sides has to carry on, it gets extended, okay? And if you've got that, then the interior opposite angle is going to be equal. Sorry, I didn't actually want to draw the arc because then it becomes messy. Okay, so that there, that's x there. The interior opposite angle is also going to be x. Okay, that's our cyclic quad theorems. Lastly, we've got our tangent theorems. Okay, the one tangent theorem also needs the center, but if it doesn't have the tangent, then it's not important. So that's why I've just left it under the tangent theorems. The radius is going to be perpendicular to the tangent. Our next tangent theorem is if I've got two tangents on either side coming from the same point, it's going to be equal. And the last tangent theorem is our surfer dude, okay, where the angle between the tangent and the chord, so that angle there is equal to the opposite angle at the circumference. Okay, that's our tangent theorems. And then the last one that does sort of sit on its own is if we've got equal chords, then we've got equal angles, and that does sometimes come up. So I'm just going to put here on its own, equal chords, equal angles. So that's if we've got two different equal chords, they're going to create equal angles at the circumference. Sorry, they're very rough sketches. Okay, so now let's go back to our diagram. They did tell us about the center here. Okay, and they've given us a whole lot of information. So we're going to make sure everything's there. AD equal to DC, it has been indicated on our diagram. The length of AC is 8 centimeters. So when they've told me that AC is 8 centimeters and that those two sections are equal, I can straight away go that that side is 4 and that side is 4, okay, because that's been given to me. Then OD is 3 centimeters, it's on my diagram. BE is equal to X. Please make sure you remember that it's just going up to the point E. Okay, and then AB is equal to X plus 4, that's all on our diagram. Okay, so what else have they told us? Oh, sorry. Okay. Let's go through everything that they've told us and see if there's anything else. The diagram has center. So if we look at our center, which theorems could we use? We do have a line going from the center to the midpoint. So that first theorem is a possibility, okay? Can I go from 2 points to the center and from 2 points up to a circumference somewhere? No, so straight away, I know I'm going to cancel that angle at center equals twice angle at circumference. The other center theorem is, do I have a full diameter? No, so I'm going to cancel that one as well. Okay, so that's what we've got from the center. They said that we've got a quadrilateral, but it is not cyclic. It's just a quadrilateral, so we can't call it cyclic. with A on the circumference of the circle. They said we've got tangents. AB is a tangent and BC is a tangent. So the tangents, if we have a look at what they tell us about the tangents, we've got two tangents from the same point, and we could possibly use, so we've got two tangents from the same point. We could use this one. We've got an angle between the tangent and the chord, but do we have a tangent and a radius? Yes, we do. So all of our tangent theorems could still get used. D is the midpoint. We've already mentioned that. E is the point on the circumference of circle with center O. So E is just saying it is a point on the circumference. So do you see we don't have any cyclic quadrilaterals drawn there? So we've got 4 points, but be careful. This fourth point is not on the circumference. Do you see we've only got 3 points on the circumference? So again, straight away, we can go to all of these theorems we've got here. Oh, sorry. And we can cancel out every single one of those. And now instead of having 9 theorems that I could possibly be using, we've only got 4. Okay, so that's what things that we can think about if we get stuck and we need to brainstorm. Okay, so let's have a look now at the questions. Now that you've got an idea of the thought process. Okay, I want to try and keep the diagram in there as well. Okay, so it says here, write down the sides of angle D1 with a reason. Write down the sides of angle D1 with a reason. Okay, any ideas? Either unmute. Okay, sorry, I must have seen this message too late. So guys, you can still have a look at A. Benati, what do you mean when you say what about E?
No, it's okay, man. I was asking before when you were mentioning the
4 points on the circumference.
Quad, yes.
Okay, cool. So it's because one of them is not on the circumference that O isn't on the circumference. Great, thanks, Benati. Okay, so write down the size of D1 with a reason. Guys, think about where D1 is. Think about the theorems that we could possibly use. Okay, and we're going to write down question A over here. And yes, straight away, D1 is going to be equal to 90 degrees. Okay, and your reason, please make sure you've used all 3 concepts. Remember that theorem 1. So this is the perpendicular, which means my reason has to use the center and the midpoint. And that will help you to figure out what your reason is going to be. Okay, so make sure you're using the correct reason. So it's going to be line from center to midpoint. Okay, that is your reason. Are we happy with that? And we indicate it on our diagram. Okay, let's look at the next one. Question B. Calculate the length of OA. So my A is just not showing. Okay, I'm so glad you guys know your Pythagorean triples. Okay, guys, because we know we've got a right angle triangle, I'm going to make sure you guys all see the right angle triangle is over here. As I said, I can highlight all over the place and undo it. And because it's that very common one, guys, I hope you don't have to do the calculation. The 3, the 4, you know the hypotenuse is 5. But if you do the calculation, it is perfectly fine. So we're going to say that OA is equal to 5 centimeters, and your reason, Pythagoras's theorem. Okay, and you write it in on your diagram. Brilliant. Okay, next one. Determine the size of angle A and give a reason for your answer. Okay, now to be totally honest, this is a little bit unfair because if you have a look at angle A, it could be this one with the cross, it could be this one with the dot. They should have been more specific. They, I think, are looking for BAO. Okay, so they're looking for the dot and the cross together. Okay, they're looking for BAO, the dot and the cross together. So what would the size of that angle be? And the only reason I could figure that out is because I looked at the mark allocation. Okay, and from my teaching experience. Okay, so we've got another suggestion that it's 90 degrees. Why would this one be 90 degrees? Tangent perpendicular to radius. Yes, thank you, Simpiwe. Okay, so BAO is equal to 90 degrees because the tangent is perpendicular to the radius. Guys, if you're not getting it as quickly as everybody else, please, I really don't want you to stress. But go back to what we basically looked at, what we crossed out, and think about what you could possibly use. So that is going to be 90 degrees. And then the last one for this question, calculate the value of x if x is greater than 1. Okay, they want you to calculate the value of x if x is greater than 1. Okay, if you don't know the full answer, but you've got ideas, remember we're working together as a team because this is completely new to all of us. So you can write that in the chat. You don't have to just give me an answer every single time. Think about, tell me what you're thinking about, because sometimes what you're thinking about, I need to help you understand that it might have been a wrong thing. But I only know that if you share it with me. Okay. So even if you don't have the full answer, I want you guys to be communicating with me. Ideas to calculate x. Yes, Michelle?
Ma'am, can I help you with the answer?
Yes, I would love that. And I so love hearing people's voices. It's so much more fun than just reading it in the chat the whole time. Yes, Michelle, tell me, what are you thinking?
Ma'am, you know that ED is equal to 2 centimeters because it's also radius, and you've calculated OA and it's 5 centimeters.
Okay, so I'm actually going to just focus on EO then. Yes, you're right, ED is 2, but because that's a radius, we know that whole thing is 5, hey?
Yes, sir.
Okay, so that's perfectly fine. That's the same how you got the ED. So that's okay. So we know that that is 5 centimeters, yes?
So, ma'am, did they give us the length of BE? Yes, it's X, ma'am.
It's X, yes.
So, ma'am, BO is equal to 5 plus X.
So BO is equal to 5 plus X. And that's literally just from our information. If you want to say radii, sorry, I'm just explaining to everybody. If you want to say radii is a reason you guys can. Okay, yes, next thing, Michelle.
Ma'am, you know that OA is 5.
Yes,
I
you
know,
know that
right?
OA is 5.
So then maybe you could use Pythagoras to calculate the value of X.
Just proven the right angle triangle. So how would we go about with Pythagoras?
X squared is equal to X plus 4 squared plus 5 squared.
X squared is equal to X plus 4 squared plus 5 squared. Are you sure you got that correct?
Yes, ma'am.
So what are the 3 sides of my triangle? What's my hypotenuse?
BO.
BO is my
BO.
hypotenuse. So remember that
Yes.
BE is X. I need BO.
Oh, sorry, X plus 5.
Yeah, there we go. Like you mentioned it earlier, so I knew you knew. But that I just wanted to stress because that was so easy to actually make a mistake in an exam. In fact, I think I seem to remember some mistake in people's exams when I was marking this question. Okay, perfect. And then you want to carry on doing that if you square a binomial?
X squared plus 25 plus 10x is equal to X squared plus 16 plus 8x plus 25.
Okay, awesome.
And then? The X squared cancels if you bring the X to the left. And then you will have 2x is equal to 16, because the 25s cancel and then you left it 16, and therefore x is equal to 8.
Perfect. Thank you, Michelle. That was absolutely awesome being able to work with somebody who was willing to talk to me. Thanks, Michelle. Did everybody manage to follow that? The main thing I want to stress that some people still sometimes forget is this squaring your binomial. Okay, guys, if you go x plus 5 all squared, there is a shortcut, and that's exactly what Michelle used. But remember that that means x plus 5 times x plus 5. And if you do FOIL, you're going to get x squared plus 5x plus 5x plus 25. And those two there is what gives you the 10x. Okay, so please remember that because there's two terms in that bracket, you can't just square everything. You actually have to do the full FOIL, or you can use the shortcut that Michelle used, which is square the first and the last term, but then that third term is you multiply the terms and double them. So that's the 5x, and then you times it by 2 to get the 10x. Okay, that's awesome. Let's go to the next question. It looks like we'll be able to get one more question done. And then you guys can rest for your weekend. I don't think there's another course tomorrow. Okay, so O is the center of the bigger circle. You've got a center. So let's quickly have a look at what we've got. Remember, we've got 3 center theorems. Okay, so if O is the center of my circle, my 1 center theorem needs the lines from that center to go somewhere to the middle or to the perpendicular of a chord. And if I look at all the lines coming from the center, do you see they're going to the end of the chord? So I'm not going to use that one. So you cross it off. Okay, so now we're down to 2 center theorems. Do I have a full diameter? Yes, I do have a full diameter. So straight away I know that that's 90 degrees. I can still use that one. Okay, so we can use that one there. And then the last center theorem is, I can go from 2 points on the circumference. Can I go to the center and go back to those 2 points and go back up to the circumference? And yes, I can. So if we go back to those notes that I had earlier, the summary of everything, at this point, I can use both of those bottom ones. I cannot use that top one. Okay, so we're narrowing it down. What else have they given us in this diagram? They said O lies on the circumference of the smaller circle. O, W, V, U are points on the circumference of the smaller circle. So here they're basically telling us, do you see I've got 1, 2, 3, 4 points on that smaller circle. So that means I've got my cyclic quadrilateral. I've actually also got 4 points on the bigger circle as well. I see bow ties in both of them. Okay, so I can use my bow tie. I've got exterior angles, and we can always possibly use the opposite interior angles. So going back to what we think about in our head, we need to have all 3 of these theorems about the cyclic quad are all possibilities that we've got to think about if we get stuck. Then we go and carry on reading. Okay, TSVU are points on the circumference of the bigger circle. We already spotted that. And they haven't mentioned any tangents. I don't have any tangents anywhere. So straight away, we can cross out all of our tangent theorems. So we don't have to worry about those. Okay, so again, we are going to be dealing with 5 instead of all 9. Okay, so that's again what you do when you're trying to brainstorm. So I am going to, I hope you guys have your question and memos. I'm going to stay focused on the picture. Okay, so the questions, I can roll down and see the question, but I'd rather just read it out to us so that, because the picture, I need it this size, otherwise I can't draw on it. Okay, it's easier to follow. So let's have a look. So it says name 4 other angles, each equal to x with reasons. Okay, so what they have told us, which didn't actually come up in the story, but we can see it in the diagram, They told us that this angle here is 2x. Okay? They told us that that angle is 2x. So we need to find something that's going to be equal to x. And we need 4 different angles equal to x. Michelle, do you want to help again?
Sure, ma'am. Oh, I didn't realize my mic was unmuted.
Oh, you didn't realize you switched the mic on. Okay, no, that's fine. Okay, guys, so let's have a look. Angle at the center equals twice angle at the circumference because we're starting at the center. So it makes sense to try and look at our center theorems. So I can go from T and U. Remember, I get to draw all over everything. Go from T and U and go to the center. Can I go from T and U and go to another one of the other angles? And I see Michelle's already typed into the messages. Yes, Banati. Okay, so angle at the center, do you see from here? I can also go all the way up to the top. And that's going to be exactly half of the 2x, which means that that's going to be an x up there. So I can straight away say that S1 is going to be equal to x, and the angle at center equals to 2 times angle at circumference. Okay. Only reason why I'm putting my reasons in 2 lines is so that you guys can see all the words. So we've got S1 equal to x. Okay, what else could be equal to x? Okay, remember all the different theorems we've got. So now we're dealing at S1. S1 was one of the points on the circumference. So maybe we should be looking at our bow tie. Michelle's given us an answer. V3 is equal to x, and that would be angles in the same segment. Looks like we're just going to manage to do all these x's, and then our time might be up. So give me your attention just for this last little bit. I'm just highlighting the bow tie so you guys can see the bow tie. But remember, we had a big bow tie for the big circle. We also have a little bow tie. Okay, so have a look in the smaller circle. We've also got bow ties in the smaller circle. Okay, yes, W1, brilliant. W1 would be equal to x. Make sure you've got the correct angle at W. And again, that is angles in the same segment. Okay, and as we go, we write it in. Okay, we need one more angle that's going to be equal to x. One more angle that's equal to x. U1. Okay, so there's a suggestion for U1. There's a suggestion for U2. Those suggestions, can you guys give me a reason?
Ma'am, I kind of thought of YouTube because of those fun angle things. I'm not really sure which one, but.
Okay, so that's not a bad idea to be thinking of that, but do we have parallel lines? I don't think they gave us any parallel lines. So be careful of that. Okay, so we've got Henry saying surfer dude. So glad my lingo is rubbing off on you guys. Unfortunately, they didn't tell us we had tangents. I don't think. Let me just, unless I missed it. O is the center of the bigger circle. O lies on the circumference of the smaller circle. Those are points on the circumference of the smaller circle. TSVU are points in the circumference of the bigger circle. So yeah, we don't have tangents, so we can't use the surfer dude. Okay, so we
Ma'am,
got, yes.
I said U2 because I could see a bow tie in the smaller circle.
Okay, so let's highlight that bow tie in the smaller circle with U2. Okay, do you see that that is going to be equal to this one? Which we don't
Oh, yes.
have the x yet. Do you see that?
Yes, ma'am.
Okay, so you just need to be a little bit extra careful about which angles are going to be equal to the bow ties. So we've cancelled out U2. We've got an idea of U1 saying opposite angles. Are you talking about opposite angles of the cyclic quad? Which opposite angles are you talking about? Opposite angles to S. Okay, but opposite angles aren't necessarily always going to be equal. Okay, I'm just double checking everybody else's suggestions to see if I've gone through all of them. Yeah, I have. Okay, so we've got U2 equal to U1 equal to X. Why do you think U2
Oh,
is
sorry,
going to...
ma'am, I meant U2 plus U1.
So you think this whole thing is going to be equal to X. What's your reason for
ma'am.
that?
Because 2x is the exterior angle of triangle OUV. And it's equal to x plus something. And x plus x will give you 2x.
Okay, sorry, because the exterior angle, okay, so you're on the right track, Michelle, but let's just make sure we got it correct. So you're using the exterior angle of the cyclic quad, am I right?
No, ma'am, of a triangle.
Of the triangle.
Ma'am,
So this
triangle
triangle over
VOU.
here,
No, VOU, ma'am.
VOU. Let me just highlight the triangle so we can all see what you're thinking. VOU, because I didn't get that one. I've got another one. Okay, exterior angle. Okay, so you're right that that's going to be 2x. But unfortunately, we don't know if it's been cut in half. Okay, we've got no idea if it's going to
ma'am,
be...
isn't two...
Sorry? So because it's... Oh, sorry. Yes, it's an exterior angle, so the whole thing will be x.
Yes,
that is fine because the other one's x. So I found this one. I'm going to tell you guys which one I found. I found that one. So it actually means there's more than one option. I found V2. So U1 plus U2 would be equal to x because exterior angle of a triangle. And then I found V2 is equal to x because of exterior angle of a cyclic quad. So yes, absolutely, that's an exterior angle. So those two are going to have to add up to 2x, and we already had the 1x. I had a similar thing, and I'm going to show you mine. Sorry, that is x, so I shall leave it there. Okay, if I go the cyclic, ooh. Okay, no, I don't know how I used a cyclic quad. So yours is right and mine is wrong. There we go. Well done, Michelle. Okay, thank you very much, grade 11s. It's been a fabulous evening.